We are live. Yay! This is Math 60, section 1.2, the real numbers. This is part 3. And my computer's trying to get in the picture. Don't you hate that? Macintoshes are all like, oh, spend all your money on me and let me in your videos. Okay, but not tonight, Satan. Okay, so we're going to talk about prime numbers. I'm hoping that at this point you have heard of prime numbers before. You've got some algebra under your belt. At some point you've taken it, but maybe you don't quite remember. Maybe you remember and it's perfectly clear. Well, let's go over it anyway. Prime numbers are numbers which are only divisible by 1 and themselves. Composite numbers are numbers which have at least one divisor, which is not 1 or itself. So basically, these are kind of opposites. A prime number, one of the most famous prime numbers, would be 2. You can't break 2 down. 2 is the smallest piece. Nothing times something else is 2 except for 1 times 2. You can't break it down using multiplication into anything else. A composite number, an example, would be the number 6, because I can break that down into 2 and 3, which are 2 other primes. So what I have done, and this is far more successful in class, but let's just play along. Let's see if we can get some excitement going. I have made a list of the set of prime numbers less than 100, but 2 of these are not prime. So let's go through and see if we can find them. To begin with, the smaller prime numbers I think are easier to think about. 2, 3, 5, 7, 11. Up till then, hopefully if you know your times tables pretty well, you'll be like, yeah, those don't break down into anything. Okay, let's go, except for themselves times 1. Let's look at these guys. Now it starts to get a little more dodgy because now we're getting further along in the times tables. 13, 17, 19. Okay, so far so good. 23, 29. Okay, so we're starting to really use your times tables memory. 31, 37. Often I look at 37 and I'm like, wait a minute. Is it 41, 43, 47? Up in here, I would probably have to use a calculator. What could you do? Let's say if you were thinking, I wonder if 43 really is prime. Well, I can either use my knowledge of times tables. Here, let me get this out of the light. There we go, my knowledge of times tables. Or I could just go ahead and say 43 divided by 7. Does 7 go into it? Nope. See how that's not a whole number? Means it doesn't go in. Okay, 43 divided by 11. How about that? Nope. So you could just try a bunch of different numbers to see if 43 is divisible by anything. It isn't, other than 43 in itself. It is prime. 47, 51, 53, 59, and then at some point, hopefully somebody is screaming at me, wait a minute, 51. Now here's the thing. I am hoping someday soon that I will be elected king of the universe. I will simplify everything. I go, basically, I've got some great offers. Everybody gets as much math as they want, and free healthcare. And also, one of my campaign promises, if someone will make me king of the universe, is that 51 will be prime. Absolutely, because this shenanigans is not okay. 51, it turns out, is actually divisible by 3. 51 divided by 3 is, look at that, 3 times 17. Now, I don't know anyone who needs to multiply 3 times 17. I think that this is actually a crime against humanity, to be honest. But as I am not yet king of the universe, we're going to have to go ahead and say, well, 51 is going to have to stay in our list of composites. Okay, so we keep looking. 53, 59, 61, 67. Again, how will you check if these are prime? Well, you Google it, or you try, like 67. You try, does 6 go into it? No. Does 2 go into it? No. Does 3 go into it? Try lots of different numbers. 71, 73, 79, 83, 89, 91. 91 is a really tricksy one. It looks prime. I mean, 11 is prime, 31 is prime, 41, 51, 61, 71. Of course, 81 is not prime because it's 9 times 9, but most of the ones are prime. So why shouldn't 91 be prime? And then if you start trying things, you're going to find that it's actually 7 that becomes a problem. 91 divided by 7 is 13. Now you could guess that someone who objects to 3 times 17 is going to object to 7 times 13. I just do. I'm pretty consistent. I don't think either of these numbers should be composite. I think we should just declare them primes and walk away. But they are, in fact. So 51 and 91 are not prime. And that leaves us with our lovely set of prime numbers. And I've made this handy dandy sheet for myself. It helps me out. Plus, I've got the happy spider at the bottom, which is like cheers me up. And something you probably noticed at this point, 1 is not on this list. Look, it starts with 2. 1 is considered not prime. It is also not composite. It is something else entirely. It's the multiplicative identity, which is pretty cool. I mean, that's important enough. You don't need to be composite or prime. You could be the multiplicative identity. Woohoo. We're going to leave it off for some technical reasons. It has to do with the definition of prime numbers and the fact that when you multiply 1 times itself, 1 times 1, the number doesn't change. So if I said, how many times do you have to multiply 1 times itself to get to 1? You can't answer that definitively because 1 times 1 times 1 times 1 is 1. But 1 times 1 times 1 100 times, also 1. So it is a complicated creature, and so we leave it out. It's not prime. It's also not composite. Okay, so I recommend you keep a list of prime numbers handy whenever you're doing fractions, whenever you're doing work with least common denominators or least common multiples or greatest common factors, all those fun things. Prime number is going to be important. Okay, so with a list of prime numbers, if you are prime, you are not composite. So 2, 3, 4. What? Oh my goodness, what was I thinking? 4 is composite. You hand me a black pen and then I'm just, just crazed with power. 4 is 2 times 2. You can totally break it down. Sorry about that. 5, 6, composite. And if you're going to say it's composite, you got to be able to say, yes, 2 times 3. Good. 7, nope. 8, yes, 2 times 4. 9, 3 times 3. 10, 2 times 5. 11, oh, 12. You could say 2 times 6 or 3 times 4. 13, 14, 2 times 7, etc. So let me see if I can cross off all the numbers on the composite list, or on the prime list. 17, then 19, then 23, then 29, 31, 33, 3 times 11, 37, nope, 41. Look at all these. Now, it's an interesting thing to notice that we keep having prime numbers, but in the beginning, they're really close. And after a while, they get further and further apart, which is kind of interesting to me. And you might wonder, has anyone ever studied that? And I would say, oh, yes. It's actually its own field of mathematics, studying how often the primes appear and whether they keep going. Because you could ask a question. You could ask, hey, do prime numbers keep happening, or do we run out of primes? Like, do all the numbers, if you get big enough, they all have factors other than 1 in themselves? And the answer is no, we keep having prime numbers forever. And that gets really important for code breaking and making. So 89, 97, there we go. So we've got our list of composite numbers. You just take out the prime numbers, and those are our composite numbers. And note that 1 is not included in either list. And you may be asking yourself, but how would I do this if I just wanted to figure out if a number goes into another number. Are there any shortcuts? And then I say, oh my gosh, have I got a deal for you? I've got something called divisibility rules. Yay! Now, this is part of the secret back alley of math. No one ever teaches this to you, which I find very strange. So I'm going to teach it to you. This is not actually in the book. Dun, dun, dun. This is free bonus math. I know. You had no idea when you bought the regular math, you were going to get bonus math, huh? Okay, so let's talk about when do numbers go into other numbers. So for twos, if the number is even, it's divisible by 2. If the number is even, it's divisible by 2. An example, the number 4 is divisible by 2. The number 1. So what is that? Those are millions, billions, trillion. 1 trillion, 111 billion, 111 million, 111,118 is an even number, and it is divisible by 2. And just as a reminder, as we're going through it, it occurs to me, an even number, let me write it up here. It ends in, what are the endings for even numbers? We're going to do it Dora style. 2, 4, 0, 2, 4, 6, or 8. Nicely done. Woohoo! Swiper, no swiping. Okay, so those are the twos. 2 goes into the number. 4 is divisible by 2. This number is divisible by 2 because it ends in 0, 2, 4, 6, or 8. Okay, talk about the 3s. 3s are weird. Now, here's the thing. We count using base 10, which, if you're not sure why we based it on 10, it's because we can count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have to make a mark. Boom. And then we start over again. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then we make 2 marks. That was the oldest, one of the oldest styles of counting. Now, does everyone count base 10? No, there are lots of bases. And in fact, if you look at your clock, you're going to see that there were a bunch of folks back in ye olden times who thought that 60 was a magical number. And that's why we get 60 on our clocks, and 60 or 360 degrees when we talk about degrees and circles. There are some groups that like base 12. There's some groups that like base 20. There are all sorts of bases all over the planet. We just happen to have base 10. And when you look at a particular base, like you base your number system off of 10s, you get some really interesting things happening. In our case, in base 10, it happens with 3. If we were at another base, it would happen with another number. So what is the weird rule? When you add the digits of the number, the sum is divisible by 3. So what? So let's take a look. 57. Don't even get me started on 57. 57 should be prime, let's be honest. But okay, so we take 5 plus 7, that's 12. 3 goes into 12, so 3 goes into 57. It's kind of weird. Let's check it. 57 is 3 times 19. Which, again, I don't think anyone should multiply 3 times 19, but that's just me. Okay, let me think of another number. How about 111? Now, 111 doesn't seem like anything would go into it. It seems to me like it would just be very difficult to work with. But in fact, let's check. How do we check? 1 plus 1 plus 1 is 3. Oh, there you go. So 111 is divisible by 3. And either you can do it longhand or 111 divided by 3. Just do it unless you hit too many ones. Sorry, I got overly excited. You know when you get a calculator and you're just like, yay, a calculator. So 111 is 3 times 37. I know, y'all had that memorized, I'm sure. Okay, fives. What are the divisibility rules for fives? Well, basically the number has to end in a 0 or a 5. So for example, the number 4,580, because it does end in a 0, 5 goes into it. The same thing with like 15, right? There's our 5. It's 5 times 3. So fives are pretty straightforward. Next up, sixes. So for the sixes to work, you have to have the 2s working and the 3s. So it has to be even, and the digits add to a multiple of 3. So let's look at a number like 18. I know that 6 goes into 18, but let me try it. Okay, so let's check. Is it even? And remember, even means you end in 0, 2, 4, 6, or 8. Yes. So the 2s are good. Okay. Check. Check the digits. 1 plus 8 equals 9. 3 goes into... So 3 goes into 18. 2 goes into 18. 3 goes into 18. 2 and 3. Oops. Let me write and. 2 and 3 both go into 18. So 6 goes into 18. Does that make sense? So you have to run the rules for the 2s and the 3s. So far, so good? Okay, let's do some more rules. There are no rules for 7. 7, you just have to divide. 8, usually we don't break things down into 8. We usually break them down into 2s. So we don't go just to 8, we go all the way to 2. But here comes 9, and 9 is right back to the weird rule. If, when you add the digits to the number, the sum is divisible by 9, then the original number was divisible by 9. So it's the same rule as 3s. So, for example, 81. 8 plus 1 is 9. And 81 equals 9 times 9. Woohoo! So what if I made a number, let's see, 36981. Okay, 36,981. Let's check it. 3 plus 6 plus 9 plus 8 plus 1 is 9, 18, 19, 27. 9 goes into 27. So 9 goes into 36,981. Now, I can already hear you asking me, saying, seriously, there's a calculator right there. So much easier just to do the division. You're absolutely right. And a lot of times, I will encourage you to use your calculators. Using a calculator, getting good with the technology, that's awesome. However, the more you can get into your head, the more you can get your head to practice doing the math, the faster you will get. So it's really going to be a decision for you personally. How far are you going on in math? If this is your last math class, then okay, I totally understand if you're going to want to rely on your calculator a lot if there's no math in your future. However, most people are going to take at least one more math class, possibly a lot more math classes. And so these things they can't hurt. They can only help you. These last three are actually very useful. If no one has pointed these out, they all go together. A number is divisible by 10 if it ends in a single zero. So for example, the number 60 is 10 times 6, right? There's the zero right there. However, you can also do hundreds. It has to end in a double zero. So there, I need another handy dandy. Here's my double zero, double zero. And if it ends in a triple zero, it is divisible by 1,000. So if you're looking for factors, you can basically pull all the zeros out right off the top, right off at the very beginning, pull out the 1,000 or the 100 or the 10. Why does it work so nicely? Base 10. 10 to the first power, 10 squared gives you 2 zeros, 10 cubed gives you 3 zeros. Woohoo. Okay. We are almost there. I know 1.2 is like the longest chapter section ever, but we're getting through it. I want to try to make sure that I've explained all the preliminary stuff. We're going to cram all this stuff into your head before we start doing algebra. So hopefully this will get you well armed and prepared to go to battle against algebra and letters and all those wonderful things. So next, we can do a little peek. The next section, we're gonna deviate a little bit. It's gonna be inequalities and absolute value, and then we're done with 1.2. Woohoo! So math on, guys. I'll see you in the next video. Woohoo, math on.